All right, so as we explored classical mechanics and the idea of inertial reference frames, when we were introduced more recently to the idea of inertial reference frames, we recognize that time and space were absolute. And then we talked about the idea that light travels at a definite speed through a vacuum. And if we look at that and we consider things like two events happening simultaneously, we found in that simultaneity mini lecture that time is maybe not absolute when we look at it with a new set of lenses in this idea of the theory of special relativity. So we're going to play with that a little bit more. We're going to do a thought experiment about time with this idea that light travels at a constant rate in a vacuum. And so we're going to explore kind of this thought experiment where we have this spaceship. Okay. And this spaceship's moving, okay? And inside that spaceship, we're going to do a little experiment where we shoot a beam of light to the other side of the ship, bounces off, comes back, and we monitor how long it took for that beam of light to go up and down. And we're standing inside that spaceship. So shoot my beam of light, goes up and comes back down. What's the time that it takes? Well, the change in time, how long it takes, we're going to call this T naught. We're going to define this later as the proper time. Well, T naught is going to equal how far it went divided by how fast it's going, right? Our velocity relationship. Well, if we define how far it goes, let's define that as a distance d. So the distance across my ship is distance d, okay? So it goes 2d, because it goes up and back, over how fast it's going, which we know is c, the speed of light, okay? So that's how fast the light, how much time it takes for this event to happen, up and back, on that ship. Okay, that's pretty straightforward. But what if I'm standing on Earth and I'm watching the ship go by, and it's going by me, right? Now let's explore what that would look like, given that the speed of light is constant. So here I am on Earth, stationary, we know what that means, right? And let's just look at this ship as it goes by. So we'll give 3 time points. All right. During that time, I shoot that light up and it travels to the top of the ship. So this is, I'm going to use this. So it does this. And then it travels back down, right? As the ship goes by. So we talked about kind of that path difference. All right. So what does this then all look like? Well, in the amount of time it takes for the light to travel to the top of the ship and come back down, I'm going to call this distance L. Okay? So in the amount of time it takes for the event to happen, shoot the light up, light comes back down, right? That event. The ship travels to L. Okay? Same distance up as it is down. If it's traveling at constant velocity, that's a key feature. So what does that tell us? That tells us that 2L, that distance, is equal to how fast it's going, we'll call that V, times how long that took. So 2L equals V delta T. Again, just my kinematics, okay? And V here is, make sure I have enough space. V is the speed of the ship. Okay? We also know, of course, that the speed of light is irrelevant of whether or not it's moving, right? So we know that the speed of light is doing something, right? The speed of light times this time, delta t. So Just the speed times the distance, the speed times the time gives me how far that light travels. So let's look at how far that light travels here on this pink path. Well, if this is D and this is L, Pythagorean theorem tells us that the light travels D squared plus L squared. That's this length. So the speed of light, this is what the ship is doing. This is what the light is doing. Okay? Because it has to go up and it has to come back down. Okay? Now if I take that, I take this relationship, 2L equals VT, and I take this relationship and I solve for delta T. I'm not going to do that math, but you can. I get a super fun equation, which relates the time observed, time here of the observing that moving, to the time of the light going up and down as if the observer was on the ship. So this is the Earth observer, this is the ship observer. The time the Earth clocks, the time the ship clocks. Okay? Divided by the square root of 1 minus the speed of the ship squared over the speed of light squared. This is a pretty fun equation. Because what does it tell us? It tells us that time is different on those two. The length of the event, this event, or any event, happens over different amounts of time. It tells us that the time of this observer is longer than the time here in the ship. Time is different in these two reference frames. That's pretty fun. That's pretty fun. Now, why is this ratio get there? Because this is v squared. The speed of the ship is always going to be less than the speed of light. Now, we're not going to do a thought experiment, but if I can travel faster than the speed of light. Okay? So, what if I can travel really, really close to the speed of light? In our normal situation, we're not anywhere near the speed of light, right? Nowhere near it. So we don't see this time dilation, this lengthening of time. We are shortening of time depending on your reference frame. We don't see it because V is so much smaller than C. And if V is so much smaller than C, then this kind of goes to 0. This is 1, and delta T equals delta T naught. Okay? But if we were moving really, really fast, what would we observe? We would observe that the moving event, this motion, is taking longer than the same event in your reference frame. So if I'm in this reference frame, this moving event is taking longer. This moving event is taking longer. So the event in this reference frame is longer than the event in my reference frame. What are those kind of implications? Well, that implication is if we're traveling at the speed of light. So what could that look like? So let's just do an example and then let you wrestle with it because it's super fun. Okay, so let's imagine, I'm gonna erase all this. I'll keep this here and I'll just kind of do it off to the side. Let's imagine that I put myself in a ship and I go traveling away and the speed is 0.999 times the speed of light. So super, super close to the speed of light. And I want to travel 100 light years away. I'm going to travel to a star 100 light years away. Okay. And you are going to wait for me to get back. All right. To get there. and let you know I got there. Yes, this is a unrealistic thought experiment. That's what makes it super fun. So what does that mean to you, to the Earth? It's 100 light years away. What is that? Well, 100 light years means that it takes 100 years to get there. So a light year is how long it would take light to travel in 1 year. Sorry, how far away it would be if light traveled for a year. How far light can travel in 1 year, okay, is a light year. And so in 1 year, light traveled 1 away, and now we have to get to 100. So it's 100 years on Earth. So this equates to the passage of time of 100 years on Earth to get to the star. Okay? It would take 100 years for you to get to that star. I wouldn't expect to hear from you for 100 years. Tell me you made it. Okay? That's how far away the star is. But what if you're on the ship? What if you're on the ship? So, on the ship is this value here, right? That's our delta T naught. So we're going to solve for that value. So, the time observed on Earth is the time on the ship. Okay? So we have delta T times the square root of 1 minus v squared over c squared. Okay, so I just solve for delta T naught. I want to remind you where that came from. All right. So, takes 100 years on Earth times the square root of 1 minus 0.999 c squared over c squared. Okay? So that's 100 times the square root of 1 minus 0.999 squared, square root, and that about equals 4.5 years. And if you do this math, you're really in meters per second, and right? So, well, no, we're in years. We're in units of years. This is an every year. Scratch what I just said. This is 100 years. So this is in 4.5 years. I don't know. I calculated it. I got 4.5. So for the person in the spaceship, 4.5 years went by. So you were on Earth and it took 100 years. That person, it took 4.5 years. That's kind of a crazy thing to think about. Right? And everything that transpires over that amount of time normally in a year is happening in a year. So it's only 4.5 years to that. Totally crazy. I love thinking about stuff like this. Super fun. All right. A couple of just sort of things to think about. A little bit more of a definition. I alluded at the beginning that this delta T naught was called the proper time. So I just want to give you that language. This is the time of the two events that are happening in the same space, same point in space. So within the spaceship, that's the proper time. That's the T naught, okay? All right? And then just to say it another way about this whole idea, this relationship, this time dilation, is that time passes more slowly. It takes longer for two events if that reference frame is moving relative to your own reference frame. So if you kind of put yourself in this reference frame, so you're on the ship, the time of that moving, because they're moving by you, right? They're experiencing a longer time. That moving, the time is measured to pass more slowly in a moving reference frame as compared to your own reference frame. The proper time again is, just want to define it clearly, is that shortest time interval. So it's always going to be the shortest time interval, this time is always going to be longer. We talked about why. Shortest time interval of the events, the two events that are happening in the same space. Okay. All right. Good job.